So this will be a group project performed in groups of 4. These will also be your writing groups, and how we're going to do this is have you choose somebody that you would like to be a group member with, and then we will pair you up with another 2 people. So the general experimental procedure for this is to create artificial foraging patches to try and lure ants in. We will be using a food source on an index card or cotton balls soaked in 20% sugar water. We will then use 3 different ones of these at different heights and count and observe the number of ants that recruit to the food patch over time. This will take place over 15-minute increments over the course of an hour. We will then count and observe the number of ants and then put them into plastic bags while wearing gloves so you don't get bitten, and then label your cards and then count all the remaining ants in that bag. So our experimental treatments will be ground level, 1 block high, and 2 blocks high. We will then combine the entire lab's data to analyze. So a good experimental design will have a manipulative experiment. It will change only the variables of interest and will manipulate each variable independently. It will also exclude as many other sources of variation as possible and will have a control. So variation in field experiments, and where do they come from? So we have natural field variation, where we have inherent spatial variations in the natural environment, like animal and plants being patchy and heterogeneous. We also have temporal variations like weather, day and night, and animal behavior. And then we have experimental variation with data collection erroring or biases, intrusion and stochastic random events, poor experimental design. So what is experimental design? It's basically how your experiment is properly designed. And you want to use this to reduce the potential effect of other variables by trying to control for variance inherent in the environment. And you want to attempt to reduce the sampling bias and variation inherent to experimentation. So in manipulative experiments, you will modify, add, or remove individual variables or a treatment in an attempt to isolate the cause and not just a correlation. As we went over in the first lab, cause and correlation are not the same. And here we have a graph showing autism in organic food sales. And although they look very correlated, they are not causated at all. They are just 2 things that happen to look similar. So in a manipulative experiment, we have a treatment, which is the manipulated variable, the control, the unmanipulated variable, the replicates, which is the repeated experimental unit of each treatment and control. And in this lab, the replicate are the number of patches placed out per treatment, and the sample size is the total number of patches that you create. So how many treatments are there? What number of replicates are there per treatment? And what is the overall sample size? This is some things for y'all to think about. So types of control. In this experiment, you should have one or both of the following. A true control, which usually leaves all variables unchanged. An example of this would be if we placed no cotton ball, nothing, we just had bare ground and we just counted the number of ants on it. Or we have procedural negative control, which mimics some aspect of the manipulation, which may also affect the outcome. So in accounting for variation with controls, some manipulated organisms themselves can cause unintended effects, which we call experimental artifacts, like disturbing animals when you move them or caging something. An artifact or procedural control can be additional control treatments that examine the effect of the artifacts. For example, cages meant to exclude certain organisms can cause shading effect on plants, which must have an artifact control. So here we have a study with ambient grasshoppers and how they eat grass. If we wanted to exclude grasshoppers, we would have to put a cage around it, but that might cause shading and therefore less growth of the grass. So we could have a cage control to examine the grasshopper exclusion that may allow some extra light in or may have holes in the side or something to where we can view the effect of a full cage on the grass. So in your treatments, you have to ensure that your variable of interest is the only variable manipulated and you should ensure that your treatments and controls experience similar conditions. This is accomplished by interspersing and randomizing your treatments. So we have an example of spatial interseparation here, where our hypothesis is the presence of owls will reduce squirrel foraging. And here we can see that there are 4 owl replicates and 4 non-owl replicates. One big problem we can see here, though, is that all of the owl replicates are placed right next to the tree line, and all of the non-owls are placed right in the open. So if they're trying to reduce squirrel foraging, well, this might not work because they're blocking out all the trees and all the open ground is open. So you don't have true variability here, and it's hard to get pure data from this example. So one easier thing that you could do is just interspersiate everything out. And now you have 2 owls blocking the trees and 2 owls blocking the field. And now we have a more true data set and something that won't cause as much variation. So you can achieve interspersion by randomly deciding where to place your treatments, like taking a coin and flipping for heads or tails, or using a random number generator. The take-home point from all of this is to make sure that each member of your group is not placing the same treatment in the exact same location around every ant bed. You also want to avoid confounding variables. So in this case, we have black and white cards placed throughout a forest. And one glaring issue we can see here, though, is all the white cards are placed out in the brush, out in the trees, everything like that, whereas all the black cards are placed right along what looks to be a walking trail. So we can notice that this treatment may not be true in the data because, you know, who knows, maybe nothing will be attracted to the black cards because people may be walking over it, or it's more bare ground or something like that. So there's a lot of variability in this experiment, and you would want to make it to where there is not. So site selection is also important because you want to keep as many variables the same as possible other than the one that you are manipulating. So pay close attention to variables in each site, like footpaths, trees, anything that might affect your experiment. And write everything down on your observation worksheet, such as GPS coordinates, weather, if it's windy, if it's a little bit rainy, where the patches are located from flora, and then also what types of ants came over to it. Now it's going to ask you for ant species. We are just looking for morphospecies. We're not looking for exact species. We don't expect y'all to know that. So if an ant is big and red and then another ant comes by and it's a small black ant, you know, something like that, you could just write, oh, those are 2 different looking ants. So we can assume that those are 2 different species of ants. So data to record is the number of ants at each patch after 1 hour, 15 minutes, 30 minutes, and 45 minutes, the time of patch placement and patch pickup, the number and species of ants observed in the patch range during the observation. Once again, we don't expect y'all to know the species of ant, just if they look different from what was already there, the GPS location of every patch, and then other metrics that will be hypothesis dependent, but may include something like food type, if there's any big trees nearby, if there's any notable human activity previously in the patch range, and any other relevant factors that may influence your data. And all data collected will go onto your optimal foraging field results worksheet, and each person should have one of these to collect their data, and each person will have at least 1 patch for each treatment to monitor.